I want to talk a little bit now about the transformation of functions. So that includes when you slide the function to the left or the right, up or down on the graph without changing its shape, or you change its shape by compressing it or stretching it horizontally, or by compressing or stretching it vertically, or flipping it over the x-axis or over the y-axis, or any combination of those things. And what the thing that does make it somewhat easier is that it doesn't matter what the function is. These transformations will act the same way on any function. And so it doesn't matter whether we're talking about the square root of x or x squared or x cubed or the sine of x. All the transformations have the same effect. So let's start to take a look at that. Okay, so let's start with x squared, for example. So we have x squared as our function f of x, familiar parabola shape. And we have a point that we can move along this function. And so let's position it here right at the vertex at 0, 0. And then we'll say, well, suppose that we replace f of x with f of x plus 5. So I set this value to 5. And you can see that I have the equation here of this new function, g of x, which is x plus 5, and then that quantity squared. So currently, with an x value of 0, our output is equal to 0, because 0 squared is equal to 0. But if we look at g of x, if we want to retain the same y value so that now instead of x squared being equal to 0, x plus 5 squared is going to be equal to 0, you can see that x has to be equal to negative 5. And so that's why the function has shifted to the left, because the point 0, 0 has now been shifted to the point negative 5, 0. Same y value, and the x value is 5 units to the left. On the other hand, if we do x minus 2, for example, you can see that our function has shifted 2 units to the right, because in order to keep our same x squared value of 0, x now has to be 2. So one way of thinking about this is, how do I solve what value of x will solve the equation x minus 2 equals, in this case, our original x value of 0? Okay, so, and again, it doesn't matter what the original point that we are looking at. So if we are first looking at the point 2, 4, our new point will be 4, 4. Because in order for x minus 2 squared to be equal to 4, x now has to be equal to 4. And that means that when we're subtracting inside the function, we're moving to the right. When we're adding, we're moving to the left. It's counterintuitive. And it's all happening horizontally. So now let's go take a look at what happens if we're doing something outside the function. We're adding or subtracting outside the function. So suppose that we start with our function x squared, and then we just add 2 outside the function. So we take x, we square it, and then we add 2. Well, our 0.24 now becomes the 0.26, because we took our original x value of 2, we squared it, and then we added 2. And so the resultant function here, g of x, is 2 units above our original function. And similarly, if I use a negative value here, my function is going to move down by 3 units. And so the point goes from 2, 4 to 2, 1. The y value goes down by 3, the x value stays the same. So when we're adding or subtracting outside the function, then it operates intuitively. When we subtract 3, it moves down. When we add 3, it moves up. All right, so let's take a look at what happens when we multiply. So we now have, again, the function x squared. And what happens when we multiply, let's say, by 2? Whereas our original point was 2, 4, because 2 squared is equal to 4, now what we want to be the case is that 2 times x squared is equal to 4. Well, that means that x has to be equal to 1, because 2 times 1 would give us 2, and then 2 squared would give us 4. So that means we've moved from the 0.24 to the 0.14. And so what happens is we've compressed our function horizontally. the bigger the value of c gets, the greater the compression is. So by the time we get to c is equal to 4, our new x value is equal to 1/4 of our original x value. By the same logic, when let's say we multiply by a number between 0 and 1, let's say 0.5, in order for this value here, 0.5x, in order for the square of that to be equal to 4, x now has to be equal to 4. It has to be twice as large as it was before. So our new point, instead of being 2, 4, is 4, 4. So that's why it expands horizontally. Now, one of the other things you'll note is that when we multiply by -1, so that instead of x squared we have negative of x, that whole thing squared, you'll notice that it looks like nothing changed, but that's because the parabola is symmetrical. And so when we flipped over the y-axis, it didn't look like anything changed. On the other hand, if we do something like the square root of x, which is not symmetrical, you can see that our original function here, which is the red function, was flipped over to be on the other side of the y-axis. So our original point, let's say, of 4, 2, where y is the square root of x, now we have to replace x with a negative value of x in order for the equation to give us still a y value of positive 2. Because now if we're saying the square root of negative x is equal to 2, then x itself has to be equal to -4. And that's why we can see this with some functions, not with others, depending on whether or not they're symmetrical around the y-axis. So a similar idea, but again with changes in what happens when we're operating outside the function compared to inside the function. When we multiply outside the function, let's say we replace square root of x with 2 times the square root of x, what happens is that our original point of 4, 2 gets replaced by 4, 4. We just took our y value of 2 and replaced it with 2 times 2, or 4. When we multiply by 3, our new point is 4, 6. And so what this means is that when we're multiplying by a value greater than 1, we are stretching our function vertically by that factor. So in this case, we're stretching it vertically by a factor of 3. If we multiply by a value between 0 and 1, we are compressing it vertically. So that our x value, same x value, gives us a y value of 1, which is only half of the original y value we had of 2 for the original function f of x. And then when we go negative here, we end up flipping over the x-axis. Okay, so those are the basic 4 different things that can change the function, but we also can start to combine them. So let's go back to our x squared, and let's look at what happens when we, let's say we slide 3 units to the left, we slide 2 units up. Notice that if our original point was at 0, 0 at the vertex of f of x, just x squared, our new vertex is at -3, 2. Because we have x plus 3 squared, which slides it to the left 3 units, plus 2, which slides it up 3 units. Now, one of the things you'll notice, again, because the vertex is at 0, 0, when we multiply, it doesn't change the location of the vertex. It changes everything else. It changes any x-intercepts we might have. Well, in this case, we don't have any. It'll change our y-intercepts, but it does not change the position of the vertex. That's why in vertex form, we have this value of a doesn't have any relationship to the location of the vertex. As I said, if we had had some x-intercepts, then in fact changing the value of d would change our x-intercepts. So notice now we're multiplying outside the function, and again it's not changing the anything to do with the location of the vertex. Now again, it's sometimes harder to see what's going on when we have a function like this, but if we look at this sine function, which we've looked at just a little bit, so if our original function looks like this, adding shifts it to the left, as you can see here, although it's not always easy to see, but it's just shifting to the left. When we add here, we're shifting it up or down. When we multiply the x value, we are compressing it horizontally. Now it's very clear to see what's going on, that this thing is getting narrower and narrower. It takes less and less time on the x-axis to start to repeat itself. And when we multiply by a value greater than 1 outside the function, it just stretches it vertically.